One is because we have this idea of, I'll draw this over here, of building services, or just we'll call it a server, and then across the network, or perhaps on the same machine, having clients that take advantage of those services. And if I build a server and I'm going to get any kind of performance out of it at all, I have to be able to handle requests on behalf of many clients.
Absolutely.
At the same time. So then I start having to become concerned with concurrency.
Absolutely.
Another reason I do have to be concerned with concurrency is that the operating system in NT is it's built different than the operating system originally was in Unix, and even somewhat different than Linux is today, although Linux is changing. The way that Unix used to work was, because multi-threaded programming is so difficult, that when you took a system call, get a little bit technical here for a minute, there's this idea of where the application runs, which is often called historically user space, and where the kernel, or the core of the operating system itself, runs, which is called kernel space. And this division has existed really in its current form since, I guess, 1973, with Unix made this very popular. And most chips today are built with this kind of model. So a system call is a request from an application for the operating system kernel to perform on its behalf. Now, when you get into the kernel, there's the following question. Is the execution on behalf of that thread to perform a system call, where can it be interrupted? Can it be interrupted at fairly arbitrary points, like I'm going along here and there's another system call that came in from a different application, so it's application number 1, application number 2, and his system call comes in, and I'm on a single processor. When do I trade off between the execution here and the execution here? Because on a single processor, I can only run one of these at a time. The way that Unix worked is pretty much when you came into the system, you decided when you would give up control of the CPU by explicitly calling the wait function and blocking. Okay, and then somebody at some other point would tell you to resume. And so it really was not a multi-threaded operating system for a long time. People started doing a lot of work on Unix over time, particularly Sequent, which was later bought by IBM, would build these very scalable multiprocessors, because it became clear with microprocessors that you could actually build multiprocessors very easily. You solve problems about the buses and the cache memories and things like that, but it became very easy to assemble multiprocessors. And so this idea of having the kernel be able to be completely multi-threaded also, so there is more than one CPU present in the kernel, but also, even on a single processor, suppose that instead of having to have a wait occur explicitly while I'm performing one activity, I might simply have the system itself choose to switch on its own. Now, normally what causes this to happen, and this is what causes rescheduling of CPUs to happen on all systems, is there's a timer interrupt that fires. And this timer interrupt says, oh, it's now, for reasons that have to do with policy and being fair about who runs on the machine, I'm going to switch from this activity to this activity. And for the most part, this switch can occur at any point in the execution. Now, that turns out to not be completely true, and I'll maybe say something more about that later, but compared to Unix, inside the NT system, the switch really could occur at any point based on a timer interrupt occurring. The reason for doing this is fairly simple, that if I don't share the kernel fairly and uniformly, it's very hard to affect a policy which would be fair to the applications that are running. And so when I used to administer Unix systems for years, sometimes an application would spend a lot of time crossing into the kernel space, running system calls, and it would be able to unfairly control the execution of the system to the detriment of other applications that were running. And so in the design of VMS from the get-go, we were very interested in being able to control and fairly schedule fairly what took place not just in user mode, but also in the kernel. Now let me just explain a little bit about what happens in a multi-threaded system. Why
That would be great.
Why I said a moment ago that you can't quite interrupt exactly every place. You have to have several kinds of mechanisms that cause you to execute your code correctly. And I'll give you some examples of how you can execute incorrect code. The simplest kind of example is, suppose I have a variable, we'll just say x, and I want x to be x plus 1. Now, this is going to consist of some compiled code that gets issued, which is something like read the value of the memory location x into some register. So let's say register 0. And then I'm going to add the constant 1 to register 0, and then I'm going to write x. Let me not draw the arrow the wrong way. I'm going to write register 0 back into x. And in the x86, since it's a CISC, or complicated complex instruction set computer, this would all be within one instruction. But these are the steps. And you notice that I'm going to read from x, and then I'm going to write back into x. Well, suppose that between these steps, I got interrupted. And this can occur for a variety of reasons. But suppose this timer fires, and these happen to be in instructions which are interruptible. And I will get the value of x into my register 0, and then another thread runs, and it happens to execute the same code. And so he's going to read the value of x into his register 0. And so suppose that x was initially 41. Now, if I ran both of these threads and they both executed this operation, what do you think that x should be when I'm done? It should be 43. But if something goes wrong in the sequence of these things, it will end up being 42. And the reason is that the first application will read in x and think it's 41. It will then get interrupted, either here or here. And the next thread will run, and it will also read in 41. They'll both add 1 to it. They'll both store back 42. And so you have operations like this that take place in the system. So when I have these threads and I have the switching between threads, I have to be sure that certain operations, of which this is one of the most simple examples, I'm able to interlock them. I'm able to be sure I don't get preempted in the middle. And there's a whole lot of techniques that we use for this. The way that Unix used to do it was actually, they had one mechanism really for doing this. And this is called something called the URCL. This is the interrupt request level. And because they had this rule that says I can only switch, so back to Unix, when I'm explicitly say wait, they knew that another thread that came through a system call would never create this kind of a problem for them. They would never be preempted because they can't be preempted. They have to give up their use of the processor. But what happens when I come into the kernel through an I/O interrupt and execute the I/O interrupt routine? Now, I can find myself executing on a different execution context, the one that comes in from here, without having explicitly said I want to wait. So I could actually switch between an instruction that was perhaps reading memory and then going to write it back. And so the solution for this is to recognize that, and this is the design of the processors to do this, that interrupts occur at a certain IRQL level. So an interrupt routine, when it starts running, runs at an IRQ level. Well, what is this IRQL, interrupt request level? What does it really do? It says that I set this to a value on the computer, on the processor in particular, and now interrupts can't occur unless they are at a higher request level than what I'm currently running. So what I can do is when I come to a place in the code where I want to do something like this, if I'm concerned that an interrupt routine might be written to also want to increment x, I can simply raise the IRQL level and then lower it when I'm done. And that's what Unix did. And we also do some of these things too at the lowest level of the system, particularly when we're outside the context of threads and we have multiple processors and we're trying to interact across multiple processors. We will start to build operations that raise the URCL as a way of keeping control of the CPU so that we don't get scheduled away. while holding locks.
Now let me ask you, because threads are problematic in many, many ways. Was that so? Who created threads? I mean, maybe who? I mean, that's not a good question, but why threads? I understand in your model how a process is a container for threads and memory space, but you know, was it necessarily in retrospect? Do you think there could have been a better model? This is totally
Yes.
speculation.
Yes.
Okay.
There
Because
can always be a better model,
Okay.
and hopefully we'll make progress with innovation in the future, and there will be a better model. But in terms of what we know how to do today, threads have been the best model for concurrency. What we're really talking about is concurrency. The other models for concurrency that exist, and there are several kinds of models, was like in the supercomputers, in the vector machines. And these were machines that would do the same operation across multiple pieces of data at the same time. You know, these are called SIMD, single instruction for multiple data. And so vector machines are a form of that. But it only works if you can structure your problem such that you want to do exactly the same operation on multiple pieces of data. So it's great for linear algebra and dot products and computing the result of scientific calculations on the computer. But for the kinds of things that we want to do in most business computing, it's not that simple. We really are in a model which is like this client-server model, where we want to be able to get concurrency. Why do we want to get concurrency? Well, because things happen faster. If you get a lot of people working on the same problem at the same time, they will get things done faster. And that's why we started to get multiple CPUs.
Sure.
And we want to be able to use the multiple CPUs to get things done. We also would like, and this is an important point to make, we'd like the programs that people write for a single CPU to actually work even if you run it on multiple CPUs. And so perhaps we could have made the simplification that says that we'll try and make it really easy to write applications without threads, but then they would never do you any good when you got to multiple CPUs. And now that we have multi-cores coming, it still is fairly clear that this is the right kind of decision. But there's another reason, too, for why you have to have multiple threads. It doesn't really have to do with concurrency or trying to have multiple servers trying to accomplish the requests of clients at one time. And this is simply back to the way this whole model here works with system calls and application threads trying to get a system service, which is that if you're working on an operation, and I'm going to erase some of this to make a little bit more room. Suppose that I want to do something that says, I'd like to read from a file, and I'd like to, say, add up, say it's a file of numbers, okay, from the file. And I'd like to, in the end, I kind of want to print the result. And by the way, I'd actually like to do this for all files of a certain class. Okay. Now, even if I'm on a single processor, threads help me get a lot of performance improvement on this operation. And the reason is this, that when I go to read the file, I'm going to block. Often I'm going to block, waiting for the operating system to go examine the file system to find the file I specified and to read that file in from disk. And while I'm blocking, nothing else is going to happen on that CPU. It's going to sit idle. And then I read that file into memory, I add up all the numbers, I print the result, and now I go read the next file. Well, suppose that what I could do is this. I could read several files at once. And so I'd say, okay, start reading file 1, start reading file 2, start reading file 3. And when each of those files completes, then add up the contents of that file. And now the operating system sees all these requests for file I/O coming at once. Now here's where most of the performance goes on a consumer desktop machine. This is your disk. And most of the performance goes into waiting for this disk to rotate and waiting for the head, I'm not an artist, as you now know, to move back and forth. That's called the seek. So there's a rotational latency, a rotational waiting as you wait for the disk to spin. And this, by the way, is why when you get a disk that's on a laptop, disks are often much slower. Okay, most desktop disks spin at 7,200 RPM. The faster disks, like for SCSI and stuff, and this is why SCSI is still used in data centers, they will spin at 10,000 RPM and even 15,000 RPM. And that means that this rotational latency is greatly reduced because you get to the data faster around the disk. And when you get to laptops, it's much more like 4,200 is like the cheaper laptops will come with 4,200 RPM, and then 5,400 if you buy a more expensive with the small drives. And so this all has to do with rotational latency waiting for the data. Now, you also have the mechanical latency of moving this head in and out also, which is like the seek time. So you have rotational latency, you have seek time. Now suppose that file 1, so I'm going to write some 1s, and maybe 2s are here, and 3s are here on the disk, and file 4. If I get enough of those requests at once, because I use separate threads to make those requests, then I can optimize this rotational latency, and I can optimize the seeking. So rather than seeking in for file 1, and then seeking back out for 2, and then in for 3, and further in for 4, I might pick up file 2 first, 1, 3, and then 4 simply by moving the heads in. It's an algorithm called the elevator algorithm. If you think about how an elevator works in a building, it doesn't let you say, oh, I'm going to go to this floor and that floor and the other floor. You all write up to the top floor anybody wants, and you write all down to the bottom floor anybody wants, because it's more efficient to have an elevator going in one direction. In fact, this is conceptually hard sometimes for people to get, because they're so used to the way an elevator works that they don't even think about the fact that there's another algorithm, which is you get in and push a button, and the order that you push the button in is the next floor. So you might go to 4, 5, and then 3, and then up to 7, and then down to 2, all the while the last guy enjoys your very long ride up and down the elevator shaft. It's not very efficient. So you can optimize those operations in terms of the seeks. You can also optimize the operations in terms of when you pick files up in terms of the rotational latency too, by saying I'll pick up the next file I'm going to see on the disk as the disk spins around. And actually this is normally taken care of automatically today by the caching. If you see like I have an 8 megabyte cache, or how big the cache is on a disk, that has to do with how much information will like scoop up as it's passing by it anyway, in case you happen to want it. So there are a lot of optimizations that happen. But the reason that this is why the determining factor for a lot of the speed on an operating system is because this is controlled by mechanical reality, and you can't like shrink it exactly in the same way you can with electronics. Indeed, the densities are higher because we can shrink how big the little magnetic dipoles are. We can shrink those, but the mechanics for moving in and out and the motors that spin this are fairly limited. It took us a long time to get here in SCSI, and we're still here on laptop drives. And if you think of how much faster CPUs have gotten over time, how much bigger memory, how much faster memory is, this just doesn't improve in speed at the same time. And so you want to be able to, in your programs, even on a single processor, you want to be able to do multiple operations at once by initiating the operation. And the most natural thing with a thread is to initiate an operation, like I want to read from a file, open a file, read from a file. When the read returns, I now have the data in memory, and now I do my operation on it. It's very easy to express that as threads. But it's also a little bit more complicated, because if I'm not careful, what's going to happen in this little program I wrote here is I'm going to end up printing out information which is all jumbled together about how many bytes, or I guess I was counting numbers, how many numbers, the sum of the numbers for each of these files, because some of them may start printing at the same time and their characters will intermix and stuff. And so before I actually print the result, I might need to take a lock. And this is where the complexity starts to come in.